Tapper, and I'm going to talk about my research creating a closed-loop recycling method for short, discontinuous carbon fibre thermoplastic composites. So the aim of this research was really to develop a closed-loop recyclable material and the relative methodology that goes with that. And the holy grail of that would be to retain maximum properties over multiple recycling loops. The methodology should fit into the circular economy paradigm as supported by Composites UK. And the reason why we want maximum properties is so that we can get maximum value from our constituent matrix and fibres that we've put a lot of effort into making in the first place. And this material we create must be suitable for current industrial manufacturing processes. So currently, carbon fibre reinforced polymers are principally landfilled. Second to that, thermosets are mechanically recycled. From this you get a low value recyclate powder, which is a really low quality. If you want to reclaim your fibres, you can use pyrolysis or solvolysis, and you can get some good properties from your fibres close to virgin. You don't really get any properties back from your matrix that's lost. But with those fibres, unless you have a remanufacturing process that's of the correct scale and the right process, you won't be able to get the random oriented fluffy fibres into enough of a orientation so that you can get a high volume fraction, which is what you need to get high performance and high value recycled components. So for thermoplastics, you normally extrude, injection mold and shred, and you can do that over and over again. The problem with that is that you degrade your polymer structure and your fibres down so much so that the recyclate is of a low value after every iteration. So the process that I developed is basically you take a thermoplastic composite, you shed that, and then you dissolve it in non-hazardous solvents. We're using thermoplastics so that we can separate those temporary intermolecular bonds in between the polymer chains instead of breaking the intramolecular bonds which cause chain scission and loss of properties. So as we dissolve that thermoplastic into the solution, we have fibres, the reinforcement fibres dispersed within that. We filter those out and then we card them and align them using the hyperdiff method. I'm glad Lawrence was actually before me because I don't have any slides describing that. But yeah, come find us at our poster later if you want to find out. So we align them into preforms, and that's really where we get our properties from, our high stiffness and strength properties from the highly aligned preforms. So then with the polymer solution, I precipitate out the powder and process that into a fine powder, and that really encapsulates the reclamation process, which is half of a recycling process, reclamation and remanufacture. That part of the process, you take your preforms and you just do simple compression molding to make your composite part again. So currently, this has all been proof of concept, and I've made some small specimens to test. I did this with polypropylene and 3 mil carbon fibres, and got an average volume fraction after each iteration of 26%. And from that, we got competitive properties, even with virgin discontinuous carbon fibre polypropylene, and to have a stiffness of 43 gigapascals and a strength of 285. And you can see from the tensile stress strain plot and bar chart that the stiffness is unwavering through iteration. But what we actually see is in the final recycling loop that the strength increases. And because the volume fraction remains the same, we think that this might be to do with matrix residue from the recycling process being left on the fibres, which acts as a kind of matrix-specific sizing, boosting that quite poor interfacial shear strength between polypropylene and carbon fibres. And we've got an increase of about 100 megapascals in strength on that final loop. So what do we do with a closed-loop recyclable lightweight material? Well, I think one of the most suitable applications for this is high-volume automotive manufacture. They have quite stringent fuel economy regulations, so they really want composites. But unfortunately, they're also stuck with end-of-life recyclability legislation. So much of that 95% has to be reused, recycled, and recovered. So you're kind of stuck with around 5% ability to put a composite in. Normally, that's actually around 20% because landfilling is seen as a recycling opportunity to a certain percentage. One of the main benefits of this, I think, is that CFRP has high financial and environmental costs associated with its manufacture, but through recycling and multiple use phases, that lightweight and fuel economy saving, you can multiply that through each time you use it in a vehicle, so that you can actually, that initial burden that you create, you offset that and you break even within a vehicle lifetime or within that second vehicle lifetime. But it also means that your recycled component is of a far reduced environmental impact and a far reduced cost, so that Automotive can start to adopt that and use that as a realistic alternative to aluminium and steel. So I've created a high-performance recyclable an inexpensive material and process, but now I want to use an industrially applicable matrix like nylon 6. I've made some specimens. I've got a stiffness of 65 gigapascals and a strength of 860. So that started off well, and now I want to recycle those and see if I can keep those properties throughout the recycling. I want to do a life cycle assessment to evaluate and quantify how much of a burden I can decrease by using my recycled components. And also I'd like to optimize things like volume fraction and adhesion further down the line. So thank you for your attention. If you're as interested in this as I am, you can ask me questions now or come find me later.